So it's with great pleasure that I'm going to present Daniela Calvetti from the University Case Western Reserve University in Cleveland, and she will talk about her results in analyzing EMG data during meditation sessions. So please, Daniela, the stage is yours, and so go on.
Okay, so thank you for the invitation, for the patience. These are, trying times here between the technology and all of the other stress. So what I want to present is some very recent results that actually have been the work which has taken about like 5, 6, 7 years to develop. And this has been part of a collaboration with Erkki Somersalo and Annalisa Pascarella, Francesca Pitoli, Barbara Vantaggi. We were all at Sapienza doing work in person together. And then there is a student, Brian Johnson, who did his master thesis on this, and he's now working at Yelp. And he really got into this, and they also got into meditation. So I thought this would be appropriate for non-invasive mathematics, because meditation, if nothing, it's one of the least invasive modes of intervening on the mental state. And I will, so yeah, before I forget, at the end I will probably run out of time. This is based on two articles, these two articles here, and the book that just came out that Erkki and I wrote on mathematics of data science. And I have to say that I got into the mathematics of data science because of this project, because there was so much data that we really didn't know how to look at it. And in order to learn to get the tools to do something with it, well, I had to study, and then I really kind of like got addicted. So mindfulness meditation is everywhere. If you do a search in Google for mindfulness, everything is mindfulness, nutrition, meditation, exercise. They even teach it in preschool these days. But the story is that from the point of view of intervention, and even at the psychiatric level, there are some conditions of the mind that maybe could be dealt with intervening on the brain. And if mindfulness meditation does something to the brain, and if is a big question here, and this has been really the motivation for this work. And of course, we're not the only people who have been looking at this problem. There is, a line of research going on. I guess what we've done here is we've approached this as agnostics, meaning that at some point we cleared the table. We decided that we're not going to buy into one theory or another one, and we were being totally data-driven, so that we would let the data tell us if there is something in the brain or not. So we started with the story of our mindfulness meditation MEG project. Started with some data that we actually got from the Pescara lab. So we had to thank them, and they had this data, and this was really millisecond resolution MEG recording from, I think there were 12 Buddhist monks in Chittarama, a monastery close to Rome. And they recorded these monks during repeated sessions of protocols of closed eye resting, samatha, which is focused attention, which essentially for those who have practiced any meditation is the breathing, breath control. So different breathing patterns. They're supposed to be calming, and they are really a transition in between regular, say normal resting state and deeper meditation. And then vipassana, open monitoring meditation, mindfulness meditation. There are in different cultures this stage of meditation, which is supposed to be the deepest, has different names, but it's pretty much contemplated by all meditators. So the question that that came to mind, and I have to say it's very addictive and fascinating, then you don't think about anything else for years, is what happens to the brain during meditation, if anything? This is a question that many people have asked, including the Dalai Lama. And that's why he has gone to MIT and offered his brain for measurements, because meditators would swear by meditation that it really puts you in a different state. I'm there with them because I've done some meditation, but it's also usually self-reported, and it's unclear when you're self-reporting if it's a placebo effect, if there is a real, tangible, measurable effect. And everybody would like to know if there is something going on. So we just joined the crowd and used non-invasive mathematics for this non-invasive methodology. So what are our data? And I'm going to do a fast forward. The previous talk was very technical. Mine, it will not be. I'm going to actually do a forward referencing for the inverse source problem that we had to solve to even get started. That took a few years to develop all of the whistles and bells for a solver that gave the type of resolution that we needed for. Because what we had is we had a lot of data. We did not subsample, so we used all of the data, so full, dense data sets here. And then for each state and each time instance, what we had is we had signal from 153 census if they were all working, and we had to invert it. So we went backwards, and we related the signal to current dipoles in source positions. And we had about in between 41,000 and 50,000, depending on the discretization. So we had, the brain densely represented with potential dipole location. And we developed a fast method that Erkki will talk about with sensitivity weighting, so that we can essentially reach deep into the deep brain, because if something makes you feel different in terms of sensation, then it's probably going to dig into the limbic system, into the center of emotions, and the center of emotions, they are further away from the skull than you can possibly be, so really towards the center. So that, that was a challenge in itself. But, once we had that, we solved this, these several inverse problems. So our data was the inverse solution, but of course we're not going to work with 50,000 location dipoles. So we decided we took a brain atlas. So we parsed the brain into 165 regions of interest. Again, we could take a Corsair dictionary, and it would work anyway. So this is kind of some sort of aggregating different regions, and the regions, in different atlas, they have different purposes. Then what we did is so in each region, we computed the sum of the amplitudes of the dipoles. And we took that as an indicator of the activity in that particular region. So right now we have kind of like for each time instance, we have a vector with 165 indicators. That's what we have. And then what we did is we went ahead, and the data were once in a lifetime, at least for us, so we couldn't repeat the measurements. These had been done a while ago. And so we multiplied, we did a multiplication, I guess, of the bread and the fish. We just multiplied instead our data by using a bootstrap process. So what we did is we started at some, randomly chosen location. And this is actually the actual entries of these are the time series at each location that we got. This is the real thing. And so we started at some, random point, and we took a sequence, we took a cut of these activities, and these are the time series that we're considering. So for example, we start here, and this is our, our first time series, and then we have this time series, and then again. So we have a randomization algorithm to start at different points. This way we can sort of reuse the data, but without biasing in our way. Now, the cuts, so we call them random cuts here, they have a fixed width, and the width is delta t, where delta t is the, the sampling rate, and times n. Now, n, this looks like, n is a done deal, but n is something, it's a parameter that we need to set. So delta t, we don't have any control over, because that's, the way in which the data was collected. N is going to be up to us, because once we started this location here, then we go n times steps. And so what is n here? So we're listening to the brain. And the way I think about this is that we cannot, so we can try, but we're not going to get anywhere. So we can try to use time slices as they are and try to make a separation of the different states, and we're getting absolutely nowhere, in the sense that each individual time slice is just some indicator of some activities in the different rows, but it doesn't have much of a signature. And the way I think about it is that you can take bags from two different urns, and you can extract, let's say, you can extract units there. If you're extracting letters, you could be extracting from the bag of Italian, English, I don't know, Spanish, but you don't know. Each individual letter is just a letter, so it doesn't tell you. But if you start extracting words, so if you start saying that you're extracting a string of, let's say, 10 letters, whatever they mean, well, then probably it doesn't take you very long to figure out what is coming from Italian, from English, from French. So we're listening to the brain, we're listening to words, not letters. So that's our best hope, to find some signature of these meditation states, which distinguishes them from like resting states or possibly these guided breathing states. So what we do is, so what we did is we decided, so we collected sequences of time slices, and I will get to how we decide how long the sequence is. And then what you do is we compute a large sample of periodograms for each state. So we have the data are labeled because we know from which session they were recorded. So for each state, we have 3 states. And then what we also do is that for each region of interest, we integrate the activity over a frequency band. So we defined frequency bands. And in general, when one looks at classic textbooks about the rhythm of the brain, there are these bands in which, sort of, which means something in terms of activities. But there are, it's a range. A band is really kind of like, it extends over a range of frequencies. And the bands that we're looking at are the theta, alpha, beta, and gamma. And they are defined slightly differently for, you see here, there are parentheses, because we had 2 subjects. So, I mean, this is a beginning. So we will have more, but we started with 2. And so the theta was in between 3 and 7.5 hertz for the first subject, and a little bit lower for the second one. And we also indicated where there was a peak activity in each band. And it was interesting because there is a lot of literature on gamma, on the gamma wave, but we didn't see any clear peak there. So we defined our bands, and then we integrated. So we essentially compressed everything in one band, again, to reduce the dimensionality of the data that we're working at. So this is a little bit of, let's say, a little bit of formulas. So this is the sampling frequency, which we do not control, 1000 Hz. And this is an indication of what's going on. So we have all of the different samples that we've collected here. Of course, we're respecting all of the different region of interest. So this is going to be 165. samples. We have P of them. And then what you can think that we're doing in this dimension here is this, let's say these plates, they define beginning and ending of the frequency bands. And we are integrating, that is to say, we're adding them all together. So we are representing each band with one value here. So we have 4 of them. So then we had to deal with all of the whistles and bells and the difficulties of the MEG data. So MEG, you don't use it raw. There are lots of artifacts that have to be removed. So there is a pre-processing, a pretty, substantial pre-processing here. And so we're removing artifacts, heartbeat, muscles, various switches there. So one may wonder whether this ICA that we're doing on the data, on the different, let's say, parses of the data will introduce some scaling that could be masking itself as a differentiation in the state, while in reality is just a processing artifact. So what we did is when we computed our power spectral densities in the different regions of interest, we actually normalized them by the DC component. That way, what we have is relative power densities in the given frequencies. That way, we're sort of avoid, or at least we are lessening the influence of the pre-processing on the different batches. So then, so again, to sort of make the point of where we are, what we have is that for each band, alpha, beta, gamma, and theta, we define the minimum and the maximum, and we record it. And then we have, we form sample matrices of bandwidth specific integrated power vectors. That's a mouthful to say here. So this is going to be our data. And so each one of them is going to be, each one of these matrices is going to be n, where n is 165, the number of rows that we have, times p, the number of samples that we have. And each column here, oops, sorry, and each column here are scaled periodograms over the given bandwidth. So this is the, let's say, the more technical part. At this point, let's say we have for each of these states, so rest, samatha, and vipassana, we have matrices that we're defining in this fashion via bootstrap, via integration, via parceling the brain and collecting all of the activities. So what do we do with this? We re-ask the same question, and now see if we can answer. So the question is, can we, now that we have collected or represented the activity in this way, can we separate the brain states on the basis of these periodogram matrices? And if so, once we do it, can we get some information about which regions of interest are more, play a bigger role in this separation? Then there is a question of the bands. People have been talking a lot about the different bands, how meditators, they have a lower alpha peak, and how the gamma plays a big role. So, is there something in these bands? Shall we, is something that agnostically we can observe or not? And then if we, so we're optimists here, if we find the separation signature, is this going to be consistent across sessions taken at different times? So these were recorded over a number of days. So we have different, let's say, different rest states, different samatha, different vipassana. So we took separate, temporally separate sessions, and we constructed matrices that correspond to the same type of steady state, but at different times. And then the next question is the separation consistent across subjects? Because this has been a major problem, and we talked with a psychiatrist, and he was like, this is what they would like, to have some consistency across subjects. So that seemed to be a setup for linear discriminant analysis in a very unorthodox way. So sometimes using tools that were developed for other applications for in a non-standard way may actually be, pretty cool and give different results. So in the spirit of data science, we started with our matrices where the data are stored as columns. And so there are matrices of rest, samatha, and vipassana here. And then what we're doing is we are defining the spread within each group, essentially, how they are spread out around the mean. So we compute the sample mean here and the sample essentially correlation. We add them all up, and this is this matrix SW. And then we're checking the separation between the different the different groups. That's the SB, B for the scatter between here, where essentially what we're doing here is we are weighing, we are representing each group with its mean. And we're weighing it by the cardinality. But right now we have equal representation in every group, so we don't have to worry about that. Then what we want to do is if we want to separate, there is this, and this is what linear discriminant analysis is all about, is finding directions that maximize the ratio here, the ratio between the in between and within separation. So we want to find directions along which the clusters, so the different classes, are maximally separated one from the other, and also maximally compact, so minimally spread out within themselves. So we would like to find a solution for this. So this mathematically, this is a standard generalized eigenvalue problem. It has to be solved carefully because it has a real solution, but I mean, numerically one has to kind of go through some sort of careful similarity transformations, but it's not a problem finding it. So we were able to compute the separators. Also, the theory here of LDA says that if you have k classes, then you can compute up to k-1 separating vectors here. So we had 3 classes, we could find 2 separators here. So what we did is for each subject, so we dealt with monk 1 and monk 2 separately. We selected 2 temporally separated sessions of 1 minute of each protocol. And then we had a data set with 60,000 vectors, again with this bootstrap and integration in 165 dimensions. We computed for each one of these the 2 separating vectors, and we plotted the projection of the data. So the coordinate of these data is projected onto those 2 separators. So we have 2-dimensional, right? We have 2 coordinates, we can look at them and we can color them. And we check the quality of the separation. And then once we're happy with all of the few parameters that we need to set, then we can look at the separators and see if we can read from the separation which rows play a bigger role. So this is the choice of n. I said before, n is a parameter that we have to choose. So how do we choose n? Clearly, n equals 1 gets us nowhere. Well, n equals 20. 20 time instances are too few to say anything, to separate anything here. So here we have a sequence of what is, let's say, separators, these 2 coordinates of the 3 different classes look like when projected, when we're taking a time series of 20, 200, 400, 800, 1600, and 2000. And we see that if we want to say something here about the separation, if we want to have some hope of getting some signatures for these states, then we should actually go ahead and take our time series to be 2000 long here. And the colors here refer to the different states. So then what we have here is what I have shown here is the different, so we have sets for, so we're looking at different bands for different subjects here. And again, we see that not all bands separate equally well. So we computed the separators, clearly they separate, and now we look for each state, we look at the two separators, and we're assuming that, again, it's pretty much a consideration on what we're looking at, what we're projecting onto, and what it means for a component to be 0 or nearly 0, that components of the separating vectors that are almost 0, so very, very small, they essentially they correspond, so they identify regions, rows, because every entry in the separator vector corresponds to a row. A separator vector is a 165-dimensional vector that are insensitive. So, you know, they may be important for something else, but not for the separation. So the larger components, on the other hand, they may play a role, and then, but yet we have to be careful, because what we're doing here is we are maximizing a ratio, and the ratio is a separation between classes and compactification within the class. So they may be important for either separating one class from the other, or compactifying or clustering more, so presenting as a more, you know, packed together class. So we're not going to stretch our neck and say that this is all separation. It could be compactification. Why should this work? And
sorry for the interruption. Just to say, you have 5 minutes left.
Okay. Yes.
Thanks.
And so this is the Yale database of faces without glasses, with glasses. We run the same separation here. And we're looking at what separates, and this monster here, this is thresholded, says that, well, the separation between the two classes is really pretty much along the glasses, as we would expect. So these are the larger, say, components in the separating vectors. So confident with this, we examine the separator vectors, and we now reduce the model, because after all, you know, this is a fairly large model anyway. And so we are going to only retain the data. So we are deflating, essentially. We're projecting the data, only retaining those that correspond to rows that are, you know, of a considerable size. So we have the percentages in the paper there. And then we redo it. So we deflate the data and we rerun the LDA. Now we're going to get a reduced vector, reduced separators, and then we do it again. So we kind of like, we iteratively reduce the model, and we reduced it about 3 times. And we see that, of course, as expected, there is a little bit of a degradation of the separation, but not a loss. So we keep going until we see some separation. And again, as you can see here, this is unreduced. First reduction, we take, you know, 40, so this is the number. So the dimensionality of the vector, so we only retain 40 rows, 30 rows, and different bands, they will go. So we're doing the separation with the different bands, because, you know, they play different roles. So you see that the most separated, and this is the least separated. And with the gamma, we need to retain more than we need to retain for the alpha and the theta. So we do this, and then we repeat this with taking, so we have 2 states, 2 protocols per subject. So 2 to the 3rd is 8. So we mix, we take all of the possible combinations, and we run all of these separations among them, and then we do a tally. And the tally is the rows. So we look at how many rows stay above the threshold over the different, so all of these 8 tests here. And then we tabulate them. And we tabulate them, and this is what there is left. So this is the left hemisphere, this is the right hemisphere. And clearly there is a bias towards the left. There seem to be, the left seem to be affected more or changed more by the meditation than the right, which makes sense. And this is in the structure, so the deep brain, the internal structure here. And one subject, this is in the second subject. So now we're going to look at some consistency between the two. So there are regions that are, pretty much remaining as are being tagged as relevant in both subjects here. And the rows that are consistently represented in this brain state separators are portions of the cingulate cortex, which is, something that has been reported or has been hypothesized previously. There is a pericallosal sulcus, the insula, big times, and then several of the internal structures that remain there. So in particular, the left and right accumbens, caudate and putamen. So the striatum is, playing a role, thalamus, and the left amygdala. So some of them left and right. The amygdala is, we keep seeing the left amygdala there. And now we start looking at it, and we see that we've colored here the region, and it turns out that when we're looking at this, so what we have is that we have the cingulate cortex, which is involved with emotion formation and processing, learning and memory, and role in executive function, and respiratory control. Not surprising, because we have samatha, which is all about breathing, different breathing patterns. The insula is the big player in interoception. Right now, it's very, very big, and people are looking at how one can use this, one can change, affect it for the sense of well-being. I think it will be even more once this pandemic, once we find out how much this pandemic is affecting us. And it turns out the insula is being credited with mapping somatic states, emotion, definitely, also pain. So there is hope that meditation can be used in chronic pain control and processing, and in particular the perception of self, which is what people report after meditation, that they have a better sense of self and they're more at peace with themselves. And then finally there is all of the, let's say, the central, all of the core of the brain, emotions, but also coordination, also with the motor cortex. So, and these are the regions that we find as being relevant. So this, and again, the good amygdala, let's say, is implicated. So the conclusion here, if we're looking at the brain, and I think of the brain is just the language of the brain, there have been the rhythm of the brain, but single time slices do not say much. And in fact, we need to get long enough words to hear what the brain has to tell us. So letters, words, not just letters. And in particular, the theta and the alpha waves, they seem to play a role in the separation. So longer sequences are needed because these are slower bands. Then we implemented compression in time and space, because otherwise the dimensionality is too large and there is no meaning in this separation. There is too much space to separate. And what was interesting is that a posteriori, when we looked at our findings and we compared it with the literature, we're very much in line with what is being hypothesized. But we did not put it as, we did not use any prior here. We didn't give any region any, say, special role, any privilege over any other. And the story is that we have applied this to meditation, and the hope is that the same methodology can actually be used for other, say, being states rather than, let's say, actions or epilepsy, which are like states that are the lasting time. These are being states. So depression, bipolar disorder, one of the target would be, can we find the signature that distinguishes depression from bipolar. The pharmacological intervention is very different in the two of them, so it would be quite nice to find it. But also maybe chronic pain versus, you know, the lack of pain. And also for like studies of the type, is there something that characterizes the brain of bilingual people who grow up bilingual, people who become bilingual, and so many different possibilities. Oh,
okay.
thank you.
Thank you, Daniela, for this very nice and interesting talk. I think we have time for just one very quick question. Is someone in the audience that have a question? If not, I have more a curiosity than a question. As you say, and I can guess, these are once of a lifetime data, but which kind of data they are? They are like very noisy data or very clean data? Because, for example, I can imagine that Buddhists are very calm in the EMG sensor, so you're not gonna have head movement, for example, I guess.
So these are relatively, so they are not as bad. The data are not as bad as they could be. But we already see a difference between subject 1 and subject 2. There were more, let's say, issues with the recordings of subject 2, and all of the problems with MEG data remain there.
Okay.
So still, you know, you need to pre-process the data. And what we tried to do, what we had to do as we were going through this, we kept asking, you know, we do not want the pre-processing to be used as, so there is a typical example of a classifier that was classifying very well Russian and American tanks, and then it turned out that the Russians were always out when it was cloudy, and the American ones were always out when there was the sunshine shining. So we wanted to avoid that we would get that kind of, you know, we wanted to avoid that we would be fooled by some pre-processing artifacts, which was the reason why progressively we developed this relative periodograms. So we divided by the DC. Initially, we started looking at the DC, but it looked like, you know, this could be, there could be more there that, than just an activity of the brain. So it could be a processing, a signature of the processing, and we cannot avoid that. So, but normalizing, everything is relative, so it gives us a little more confidence that.
Okay. Okay, thank you very much again, a virtual club. And so I think we can go on.